The moment I did a problem, I select using implicit. So you take the equations. No, first of all, I need to understand the surface that we are talking about, the problem, no? And that problem we are talking about sketch. Sketch is super important to have some idea, geometry idea, what problem you are facing now. This is a sphere, right? Yeah, a sphere, totally full sphere. Full sphere. Full sphere. Full sphere. Now full. No, not like that. It's, let me see. Okay, sphere. Okay, hello. Okay. It's a sphere. In any optimum, no limitation. Now the top and the bottom. But the bottom not important because we have another condition in the surface is above the plane C equal 1. Okay, the radio of this sphere is obviously radical 2. So this distance is radical 2, and radical 2 in decimal approximation is 1.40 something, 1.41. However, we have a plane N1. So this plane N1 is parallel to the XY axis, cut off the sphere in one specific part here, okay? And this is our surface. Our surface look like a hot. Okay, this is 3D view. See, I want to do 2D view, 2 dimension, to understand much better. And remember, you can do a lot of 2D view you need to understand the figure. For example, one is suppose a sphere like that. I suppose this is x-axis. I suppose this is z-axis. That distance is radical 2. Okay, and we have a plane that cross this, and this distance is 1. This distance is 1. Okay, this is radical 2. This is also radical 2. This distance, this hypotenuse is radical 2. We have a triangle here. Okay, the hypotenuse is radical 2. This distance is 1. I suppose that this distance horizontal is 1. This is 45 degrees. So this is angle pi over 4. You know, que es pi over 4? You apply trigonometry, no? Now, in the projection onto the XY axis, well, to say I suppose case, looking the C equal 1, so you plug in 1 here, in the equation we have x squared plus y squared plus 1 squared, que es 1, equal to, therefore, x squared plus y squared is equal to 2 minus 1, que es 1. It's a circle. It's a circle with the center and the origin, and the radius, que is 1. And this radius is 1. 1, negative 1, negative 1. Entonces, es very, very important to do this sketch, to be familiar with the surface that I want to compute, right? And what about ds, this famous ds? How we compute ds? Well, there are many ways. In this paper, I did in that way. I make a decision to apply implicit. I don't know why. It's one formula, one possibility, implicit form. To apply implicit, we need to take our surface and write like that. Capital F, x, y, z equals 0. Entonces, our surface, you move everything. This is x squared plus y squared plus c squared minus 2 equal to 0. And you compute the gradient of this capital F. Okay, remember gradient is a vector, and you differentiate partial the x with respect to x, comma, partial the capital F with respect to y, and partial capital F with respect to z. Es obvio, es too easy, es 2x, comma 2y, comma 2z, and this 2 is a constant, do not participate in the game, and this is the gradient. You want to find the magnitude of this gradient. Oh no, this is not vector, f is scalar function. Okay, it's gradient, entonces es square root, everything is square, 4x squared plus 4y squared plus 4z squared. Okay, entonces you seek a fourth common factor, factor out outside is like a 4, but outside the radical like a 2, no? And we have square root x squared plus y squared plus z squared, no? But I know que x squared plus y squared plus z squared in my surface, que is this, is equal to, actually we discovered that this is 2 radical 2. It's a constant, 2 radical 2. Makes sense, right? So I come back to the formula. Okay, the formula for the ds is a magnitude of this. Okay, by the way, fortunately, it's a number, it's a constant, divided by magnitude of this dot product K. And this is when you are doing with the dot product K, this is dx dy. So you select another unit vector, so your projection on the plane, pero K que is perpendicular to the xy plane is dx dy. Entonces now, see, you are doing the dot product of the, look at that, of this gradient. Okay, is this dot product K, que you know very well, que K is 0,0,1 unit vector, no? It's obvious that when you are doing the dot product and between these, we have only to see is that part. So far, the formula for ds is 2 radical 2, is this, divided by 2c dx dy. And 2 is cancelled. Basically, our surface area is the double integral. In this case, yeah, it's a double. Because when you apply this formula, the differential is dx dy, entonces is no surface area anymore. No. Entonces, in the region R of radical 2 over c dx dy. Okay. Now, who is R? The region R is a projection of the our surface onto the xy plane. Is this? It's the unit circle. This is the region R. Okay. Suppose that this double integral you ending like a polar, right? Like a polar. In polar, I need to set up the limit in the polar. Suppose que ending in the polar. Pero sí, see in polar, I never see before. Well, yeah, I see because in the original equation for the surface, look at that. C squared, look, I take this one more time. X squared plus Y squared plus C squared. So I need to do something is equal to 2, no? And polar, x squared plus y squared is r squared plus c squared equal to. Therefore, c alone is square root 2 minus c squared, minus r squared, sorry. R squared. Because I need to write the integrand function using the variable que participate in the polar, que is r and theta only, right? Therefore, my equation so far is radical 2 divided by radical 2 minus r squared, que is c, the Jacobian, because you transform the Cartesian xy to polar, is r dr d theta. R dr d theta, much better. R dr d theta, the very, very, very popular Jacobian and polar, no? Okay, you are super familiar. And the limit in this case is, in this figure, is clear, okay, from 0 to 1 and from 0 to pi. Okay, I don't want to waste the time solving this integral. I promise I did. No, if you trust to me, you get the answer. No, this is another job completely different to the calculus 3. Okay? But you know how. Okay, we are doing several times. Not too much, but we are doing. The answer is 2 pi parenthesis 2 minus radical 2. Boom. Final answer. And this represents, guys, the surface area expressed in the unit que the problem is given, que the problem in mathematics do not specify unit, but in engineer, yes. Suppose que this is a meter, so this is meter, square meter, right? Because it's surface area of the one surface que is a little bit curvy, because it's a portion, it's a key portion of the one sphere. Cool? Do you understand or no? No? Confusing? You follow me? Oh, come on. It's important for me that you answer me and take advantage and try to ask questions. Come on, come on, come on. Opinion. Opinion. It's no big deal. It's just formulas. Of course, you need to know everything. You need to know the interpretation, the three-dimensional surface, and the 3D space. You need to know the double integral. You need to know polar, and the rest is the complementary part is the formula, specific formula for the surface integral. Okay? Come on, say something. No? Quiet. Lola, say something. David. Álvaro, que you always. Daniel, Maximilian. Okay. And guest, I don't know who is a guest. No? Wow, it's frustrating for me. Can you teach it with the student and the student don't talk to me? A ver. Sound good. Okay, Álvaro dice, sound good. Okay, so Álvaro, let's do it. Entonces now, no more surface area. No. Let's compute the surface integral in using a scalar function, no? And the interpretation, for example, example 1. Let me repeat again the interpretation. Now I change, no surface area anymore. Now we have, suppose compute this surface integral, x squared y, c this. Okay, this is my integrand function. No one, integrand function. Therefore, the interpretation of this, que I suppose always gets the density function, In this case is surface density. Entonces now the interpretation, the answer que give me this double no surface integral, sorry, is the mass. The mass of the something, one surface, and this is the density. Do you understand the idea or no? And what is the S? The S is given also, no? It's important. Is a plane C equal 1 plus 2x plus 3y lie above this rectangular is 0,3 cross product 0,2. Ese rectangular. Okay, on the XY axis. Okay, we have a plane. Let me try to understand. We have a plane. I have no idea. Pero es easy in GeoGebra, and put in GeoGebra. Pero no. We have a plane. Like that, boom, plane. However, I want to compute that surface integral. And one specific region que es in between 0 and 3. This is X. And this is Y, right? And 0, 2. Okay, something like that. Okay, this is my projection, maybe, no? However, I want to find in this, I'm using another color. Okay, here. Okay, basically, it's a plane, but si you write this plane like that, I suppose it's infinity in every direction, no? Pero no, I want a lamina of the, I don't know what metal, what material, specifically here, que lie on this. Okay, do you understand the idea? You understand the idea?
Yes.
Okay, cool. Entonces now, in this problem, I select the explicit form because I consider it easy. And the formula for the explicit form is dx is a square root fx, so partial derivative f. In this case, who is f? F, so you make a decision, use explicit, you always believe in your imagination que z is f of x comma y. Okay, f of x comma y is this equation. Okay, entonces you differentiate with respect to x squared, es a formula, and with respect to y squared plus 1. And this is dx dy. Because finally we ending in one double integral. Okay, the differentiation f with respect to x is super easy, it's 2. Yes or no? You differentiate this expression with respect to x is 2. And you differentiate with respect to y is 3. I'm plugging in. So basically we have ds is equal square roots 4, 2 squared, 3 squared, 9, plus 1, dx dy. Then 14, square root 14. Basically, wow. ds, our famous ds, is square root 14 dx dy. In this moment, I would like to interpretation the dx is infinitesimal surface area, but on this. Suppose this is square. And dx dy is infinitesimal also, but on the xy plane. And this specific problem, the relationship, so the scale factor between this area and this area is square root 14. Because obviously this plane has some inclination, no? So it's not equal area. This is the magic of that part. And finally, I set out my surface integral like that. But now this is in the region R, no S, because you apply the formula which do the projection on the XY plane, no? So now I copy x squared y is the integrand function, but C no, because it's a double integral que participate only x and y. Pero what is the connection? This is the formula of the connection. C, no C anymore, is 1 plus 2x plus 3y, and ds, que ds is square root 14, it's like a Jacobian, no? dx dy. Okay, you know, the interpretation for the Jacobian is the scale factor, no? In between when you are doing transformation, right? Everything matching, everything is good. Now, I need to set up the limit of this integral. Well, it's easy because, okay, so you are doing, this is the 3D view approximately, you know, using my imagination, and the 2D view in the XY plane look like that. Let me see. Is XSM between 0, 3, 1, 2, 3, and Y2, 1, 2. It's a rectangle. That rectangle. No, this, that rectangle. Okay, it's this rectangle, no? Okay. It's super easy. The limit in our double integral is, suppose que I make a decision. In this case, either way, in this case, I accidentally, I suppose that the order of the integration is like that. Because I copy dx first. Okay, the dx go from 0 to 3 to 3, yeah. And y, when you extend the window in that direction from 0 to 2. Boom! And the answer is, when you put in a calculator or you are doing by hand, but you spend 20 minutes doing this, is 171 square root 14. And the interpretation of this is not surface area. No. It's a mass of the one hypothetic lamina represented by this surface in which the density function is this function. Make sense? Make sense? It's mass. Yes. Okay. One more time. I don't know what is the reason that you don't understand very well. You see how magically when the integrand function is 1, you reduce the dimension of the problem. Now, in this case, the integrand function is not 1. It's one function that represents the density. This is completely heterogeneous lamina. The mass in different points is different, no? And si it's constant, it's easy. You put the constant and you put outside. The majority of the problem engineer is the density is constant. But no, suppose one lamina gets formed by the metal and the wood. That half. So now the density is a variable depending the position in this. Okay. So now in this case, obviously, when you compute the surface area, it's give me the mass of the one lamina. Lamina, you consider mathematically is not solid. Lamina is one hypothetic solid in between quotation marks, in which one dimension is negligible, right? Because is to the thickness is too small. and the other dimension is bigger. Entonces, en your engineer mind, you believe que es lámina, right? Do you understand or no?
Yes, I get it.
Excellent.
Thank you.
Okay, one more example, a little bit different of the surface integral, in which the integrand function is scalar, pero no one. Example 2. In example 2, we have this surface integral, okay, and the function is xy plus 1. This is our integrand function, ds. Who is this? Bueno, es surface formed by this surface. C is equal x squared plus y squared. Okay, you are super familiar with this, but specifically inside another surface is x squared plus y squared equal 4. You recognize que this is paraboloid, yes or no? To have some idea how it look like. My problem. It's a paraboloid. But if you put in algebra like that, you see paraboloid que open up, paraboloid, like that. But this is totally infinity in the c-axis. Continue forward. However, no. We have here one cylinder. Okay, by the way, the radius is 2. Cylinder. The radius is 2. Which, well, suppose hypothetically, the radius is 2. No good, this is sketch. Erase. Okay, cylinder. Okay, no down, because you know que C is always positive because the sum 2 square. Entonces, cylinder, circular cylinder, a little bit, and the paraboloid in one moment touch the cylinder, and the area que I want to using in the problem, so this surface, sorry, area no, surface, is this surface, is the surface in the, so the surface of paraboloid, pero que es just inside the cylinder. O sea, the part que continue forever here in that direction, no, it's not considered. Okay? And the top, no, it's totally hollow. It's totally hollow. Okay, it's something like that. I have the sketch in GeoGebra. Okay, let me show you. Let me show you the sketch in GeoGebra. But it's easy to understand, no? It's easy to understand because it's a paraboloid. Let me try to find GeoGebra. Open surface integral with scalar function. Okay. Let me share the screen. Share. Do you see GeoGebra or no? Not yet. Do you see or no? Yes, Álvaro. Look, Álvaro. Okay, the first equation I select here is the equation of the paraboloid. Look, it's a paraboloid, but this paraboloid is infinity. Now I'm doing the cylinder. Boom. Okay, you see? Now, the area I want is the no intersection, no, es the part of the paraboloid, but inside the cylinder. Okay, so now actually is this area. Bam. Let me delete cylinder, let me delete this. Do you see? Do you see? This is the area that represents our problem. And by the way, this is the line or the curve bound above. I want to take advantage this moment to explain how. And when the class is over, I send this script in GeoGebra, and you can see how I create that using the command curve and the command surface. This is a little bit, I understand it's a little bit complicated. Because you are familiar, for example, you put directly the equation in GeoGebra, boom, but this equation have no limitation. We have no start, no end. Entonces, now GeoGebra understand que es el paraboloid de infinity. No. This is a surface que have bound. Do you see or no? Do you see? Yes or no? Cool. Now, Alvaro, look. We come back again to the whiteboard. I want to take advantage of this moment to explain why not. To explain the command in GeoGebra to see this. Okay, look. You copy surface. You copy surface. Surface and curve. Okay, curve is this. The intersection, no? And the intersection between this and this is obvious. Es obvio que es a circle. Si you suppose que x squared plus y squared is equal to c, and x squared plus y squared is equal to 4, it's because c is 4. Or x squared plus y squared is equal to 4, and the plane x, y represent the circle. It's obvious, right? Represent the circle. Circle. This is 3D picture, but in 2D picture, but we're here. In 2D picture, 2D, we have circle where the radius is 2. Right? The radius 2. However, how you do in 3 dimensions this circle? Well, you put a curve, and the curve you put in parametric, but the parametric is super easy. It's 2 cosine t, comma 2 sine t, comma t, no, comma 4. Okay, remember we are talking about 3 dimensions. This is x, this is y, and this is z, and CF4. Look. Comma t, because we have only one parameter, because it's a curve, no surface. Comma 0, comma 2 pi. You understand very well this or no? And magically, when you put this command in GeoGebra, wow, you see the curve, that curve, in the 3-dimensional space, and the C high F4, and it's a circle with the radius 2. Similar idea, we create surface. So that surface, you create using the parameterization also, but in this case, the surface, the radius no is constant, it's a variable. And you declare as one variable, que in GeoGebra I like to call U and B. In the real life, to understand much better in the paper, I call another name, maybe R and theta, I don't know. You put, for example, R cosine theta, comma, R sine theta, comma, R squared, because it's a square. This is R squared, C. Remember again, this is X, this is Y, this is C. Now you declare the theta, and because it's full ellipsoid no, paraboloid, is in between 0 to pi, comma, r go from 0 to 2. Okay, because it's a radius. 0 to 2, 0 to 2 is exactly when you ending in 2 is the curve. And these generate any point inside the surface. Do you see or not? At the beginning, it looked like weird. However, it's super easy. Intuition, imagination, right? Now let's continue the idea for the parametrization. So in this problem, I make a decision to do the problem using parametrization. So the parametrization of our surface is vector value function, okay, depending of r and theta, is r cosine theta, comma, r sine theta, comma, r squared. And you know that this represents paraboloid. This is the same of this. This is in the language of GeoGebra. And this is the language of the piece of paper. And your computer, wait, don't forget to say R domain is in between 0 to 2. And theta is in between 0 to pi. I don't know why I like so much do the sketch of this. Because this is theta, this is R, so say it's from 0 to pi, and this is from 0 to 2. This is totally rectangular, eh? This domain, issue, rectangular, domain. Okay, ready. The formula for the ds and parametrization is, let me copy here, ds is r, and the parametrization is rr cross r theta, actual value is dr d theta. It's the formula, no? So let's do it. Let's do it quickly, of course. RR is the partial derivative, this vector value function with respect to the R, and this is cosine theta. You differentiate with respect to R, and theta you consider a constant, no? Sine theta, comma 2R. It's easy to differentiate that. And R with respect to theta is, to differentiate now with respect to theta, is minus R sine theta, comma r cosine theta, comma 0, because the last component is z, do not depending of theta. And when you are doing the cross product of this, okay, you know how you are doing the cross product. You're using I, j, k, and you copy cosine theta, sine theta, the component for the first vector, the component for the second vector, okay, and you apply the determinant, cosine here, cosine theta, and 0. I skipped that part, of course, and the answer is a vector. So obvious, no? There's a vector minus 2r squared cosine theta, comma, minus 2r squared sine theta, comma, r. And when you compute the magnitude of this, you have a square root. This component is square, okay, it's negative but become positive. It's 4 r to the 4th power cosine squared theta, plus this component is squared, is 4 r to the 4th power again, pero sine squared theta, plus square this guy is r squared. And do you factor out here? Bueno, 4 4 r to the 4 power, no? And you have inside the parenthesis cosine square plus sine square, que I know get 1, plus r square. Now one more time, you factor r square, okay, you get what is r square outside in one new parenthesis or outside the square root, like only one r, and stay inside here 4 r square plus 1. Do you follow me? Do you follow me?
Yes, we follow.
Okay, cool. Now, finally, we have the double integral in the region R of the integrand function, que es r square root 4 r square plus 1. And the variable in our game is, well, wait. Okay, I forgot the integrand function. The integrand function is, I forgot this integrand function. This integrand function is xy, but I need to express it like a polar, no? Polar. And polar is, okay, our integrand function is multiplication x and y. But I know very well the formula. X is equal r cosine theta. Y is equal r sine theta. Entonces instead of x and y is x times y, que es x squared cosine theta sine theta plus 1 multiplication by the ds, and ds is this guy, is r square root 4r squared plus 1 dr d theta. Okay, guys, I notice in this case you don't need to apply Jacobian. You say, oh, professor, what? Okay. So you are doing the projection here into this circle, no? But this is the substitution directly from this problem to polar. But in this case, I am doing the parametrization. Entonces now my region is not a circle, no. My region is the rectangular. Do you see the idea? Okay. In this moment, it's important that you understand the difference between change of variable. You change xy c to polar, or xy to polar. In this case, parametrization, que is another thing different, but I don't know if it's the same or no. I want to discuss in your moment if it's the same or not. But in this case, not necessarily Jacobian. Do you understand not necessarily Jacobian? Because my region is not that region, sino that region. Okay? It's another way to change variable. Parametrization. Okay, cool. But what about the limit? Well, the limit is super easy. The limit is r and theta. Entonces, r vary from 0 to 2. Look at that. Suppose I integration in this direction. And theta vary from 0 to pi. Okay. This is no big deal to do by hand this, but I don't want to waste the time with this. Okay. The answer is pi over 6. 17 radical 17 minus 1. Here's the final answer. Okay. Notice So you make a decision to do the problem using parameterization. Maybe it's too long, a little bit, because you need to compute the cross product. But actually, you transform it, our surface, que es a piece of paraboloid, to another surface, que es rectangle. Okay? No, it's different idea to, when you change a variable, you transform this surface, or you project in this surface paraboloid to this. This is change of variable, and this is parameterization. Look. Do you understand very well this or no? Complicated, eh? A little bit abstract. Question, guys. Question. Entonces, now, remember, the most important is you have three different ways to compute the surface integral, que es explicit formula, implicit formula, or parameterization. And you suppose that you don't know exactly what way you want. You start, you select one. And in the middle of the process, you see, oh, it's too hard because the integral I need to solve it is horrible. So now you switch into another way. No, it's a one possibility, right? Okay. Now, we continue surface integral, but this surface integral is the vector surface integral. Vector. Remember, we have studied vector calculus. Vector surface integral. What is the idea? What is the new idea behind this? Well, the idea is that now the integrand function is a vector field. Okay? So basically, we have surface. Basically, we have vector field. Capital F in 3D. Of course, we have normal vector, uninormal vector, and we compute the vector surface integral. So basically, the thing is, you compute the surface integral of the vector field dot product univector ds. And this cross product indicate the integrand function that we using to compute flux in 3D. Flux in 3D. Remember, what is a flux? A flux is how much vector field crossing the surface. Okay, remember, so you have, for example, let me set up example. You have, for example, this surface. Let me try to do easy, a plane. And we have vector field like that. And I suppose that the unit vector is this. And this is super important moment, guys. This is the orientation. So you assume the red part is the normal vector. You assume in this, or no, you assume in opposite direction. I suppose I want to compute the flux leaving the surface. Oh no, I want to find the flux go inside the surface. So the orientation, in what direction you prefer to compute that, or you need to compute that, you define. It's totally free for you. Okay, so now, suppose another scenario in which you have, for example, no. Suppose you have again a plane, but the vector field now is in opposite direction. And the orientation, why not, is in this direction. Suppose another scenario, okay, we have a surface here. We have now the vector field in this same direction, but the orientation is like the original, no? Okay. And suppose one last scenario in which the orientation again is in this direction, and the flux, and the vector field is in this direction. So the thing is, determine the sign of the flux. Remember, flux is the amount of vector field crossing the surface. Flux, 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 and flux. What do you think about the flux in the first case? That one, number one. ¿Es positive or es negative? Opinion. I need opinion. You are familiar with the dot product. It's no secret for you. When the angle in between the vector que perform the dot product is acute, es positive. Si es obtuse, es negative. Si es 90 degrees, es 0. Orthogonal. Yes or no? Yes or no?
Yes.
Entonces, what in the first scenario? What do you think about the flux? The flux is positive or is negative or is 0?
Positive.
Absolutely, it's positive. It's positive because look at the angle formed by the blue. I don't care, it's a bunch of vectors. It's a vector field. I know, you know. It's obtuse, therefore the flux is positive. What about the second scenario? What do you think about the second scenario? The flux is positive or negative?
Negative.
It's negative. No, I don't think so. I put intentionally to positive. I put intentionally to confuse you. It's positive because the angle formed by the blue. Let me extend a little bit to see clear. It's obtuse. Here, obtuse. So it's also positive. And what about the third scenario?
It's negative.
It's negative. And what about the last scenario? Well, using your imagination, this is 90 degrees, no?
So it's 0.
It's 0. Remember the famous example, you have a bucket or you have the container. I want to investigate how much water. See, this is the waterfall. Go in the container. This is the area, and the vector surface area is perpendicular, no? This is the normal vector, no? And this is the vector field. No water, no water. Makes sense. Do you understand very well the flux or no? It's very intuitive idea. So you understand this, you have no problem because the formula is similar. Okay, one more detail. One more detail. This is the formula. The formula somehow involves the normal vector, uninormal vector. M is uninormal vector. And some book, a person I like, write this equation a little bit different, que es vector field that ds vector. And the x vector is m vector multiply, not dot product, multiply, just regular multiplication. This is the vector ds. ds is a scalar. Scalar, tag vector, and ds is like a infinitesimal area vector. Okay. infinitesimal surface area vector. Okay. And now we study now different surface, you know, plane, sphere, cylinder, and we compare why not the normal vector. Okay, but before that, I want to explain one super weird thing. Pay attention. I have a video in YouTube, 4 video. Okay, want to see a short video. Because the majority of the surface we have in our real life is orientable. So orientable surface means que the surface have 2 faces. Okay, suppose the typical example of the plane, we can define, if you want, one normal vector in this direction. This is the orientation. Okay, one in this direction. 2 faces, 2 possibility of the orientation. However, we have another weird surface that is non-orientable surface. Okay, we have no 2 faces. We have only one. Okay, I want to explain. It's weird, very, very weird. Entonces, we have 2 examples. The first example we want to study is Mobius. This is the Mobius strip. Mobius strip. It's a strip. It have only one face. Weird, super weird. And claim bottle. Claim bottle. It's a bottle. Okay, have only one surface. I want to represent 2 video first. Video about Mobius string. And the first video you see how we make the Mobius string super easy. And in the second video you see what is the idea. Okay, this strip have only one face. So the idea for the first video is to make Mobius string. And the idea for the second video is understand. Okay, we have only one face. And likewise happen in the claim bottle. Okay, bottle we have 2 video. In the video 1 you see how you make. This is very, very complicated, but no, it's okay. In Amazon is sell the claim bottle like a ornamental object, and the price is only $100. No? Of course, of the glass. And another video, can you see the proof? Another proof, you know, the animation. What is the reason that this bottle look like bottle like that? Have 2 faces. In this case, this is not a claim bottle. This is the ordinary. Okay, we have the outermost and the innermost. We have 2 faces, no? It's a glass. Okay, so let's try. Let me go to the YouTube. I want to share with you this. Okay, YouTube. Of course, I save this. And let me know if you hear well or not. Okay, bookmark. Okay, we have one of the how make Mobius string.
Algo te detiene. Oh. Sí.
Okay, let me try again to share the screen. Okay, here, over there. Switching to YouTube. There you go, YouTube. Do you see YouTube? Do you see YouTube?
Yes, we see YouTube.
And you hear the music or no?
No.
The music no? No? I suppose if you hear my voice, you hear the music, no? No the music. But it's completely illogical because by my microphone, see I hear in my okay. Well, okay. I want to explain.
Professor, I don't know if you can hear this, but we can barely hear you right now.
It's the most important moment here. Wow, this is a Mobius strip. Do you see? Ahora I want to show you in another video. Okay, do you see another video? Mobius strip. Do you see another video?
Yes, we see it.
Okay, cool. Now I try to rotate around the Mobius strip one ball. And you see that we have only one face, not two faces. You see? Do you understand now? Entonces we have only one normal vector, not two normal vectors. So it's non-orientable surface. Do you understand the idea? Yes or no?
Yes, we understand the idea.
Excellent. Okay, let's move. Let's move on to the famous claim bottle. Claim bottle is more complicated. Pay attention. Claim bottle. Okay, there you go. Claim bottle. Do you see claim bottle? We have rectangular. We have rectangular, and we moving this in a weird way to create the claim bottle. Look. Wow. No, I like so much the music. The music is terrific. Do you see the idea, no? The shape of the claim bottle. Yes or no? In the next video, I want to show you how the the claim bottle have only one face. Entonces, for this, the video uses a book, walking around the cake bottle and put inside every place of the bottle. So we cover every place. You don't need to switching because this bottle have only one face. Okay, look. Wow. Again, repetition. It's a walking around, go inside. I don't know if I go outside again or no. I don't know. I have no idea. No idea. Walking. Go. Outside. Do you think we have only one face? Do you see or no? Tell me. Yes, Alvaro. Wow. Fortunately, guys, the majority of the surface is orientable. So we have a normal vector in only one direction, two faces. But I try to bring this an interesting example of this. Okay, cool. This is curiosity, not always is mathematics. This is actually mathematics. But again, very cool, Alvaro like. Alvaro, I want to send the link for this video to you see watching again in detail, okay? Okay, let me try to come back to the whiteboard again. Okay, there you go. Entonces now, what is the formula, professor, to compute the flux in 3 dimensions? Well, as always happens, because the flux in 3 dimensions is computed using the surface integral. We have different weight. To say, I want to start the most important way to compute the flux integral using surface integral. So flux integral in 3D is equivalent to say vector surface integral. Okay, just first of all, I want to dedicate time to compute the normal vector. Do you see the whiteboard, right? Yes or no? Yes. Okay. Cool. Normal vector, the formulas, the most popular formula is use parametrization. So you compute the RU cross product, RB. Remember, U and B are generical name. Maybe it's theta, maybe it's R, maybe it's phi, depending on the coordinate que we use, si es cilíndrica, esférica, o XY, maybe. Entonces es absolute value, this, because it's the U, the univector, no? Normal univector. It's a one possibility. Another possibility, the most popular, is compute the gradient in the implicit form and magnitude of gradient. Okay. It's a classical. We know this in the chapter 2. No? So you have surface. You want to compute the normal vector to compute the gradient under the consideration that this surface is a level surface, and this level surface, the normal vector is always perpendicular. No? Okay. Suppose a scenario, planes. Suppose we have planes. Okay, the easy surface. When we have the classical plane, for example, C equal phi, okay, it's the plane. Let me try to do my best. Parallel to the XY, no? Like that, boom, C equal phi. Es obvio que the normal vector, in this case, is equal K. Makes sense or not? Normal vector, escape. Likewise, si you have, for example, y-3, que es the plane perpendicular to the y-axis, the normal vector is j. As you have, for example, c equal 1, the normal vector is I. Make sense? Make sense or not? Entonces, one problem, easy problem, que you see normally happen, que es a classical plane que have missing two variables, que es parallel to the one plane, xy or xc or cy. Entonces, now, to find the normal vector, well, it's easy, o es k, o es j, o es... bueno, no, okay. So you have another plane que es inclined plane, like that, you know very well, ax plus by plus cz equal d. Suppose the generic plane, no? In which nothing is missing. When you know very well que the normal vector, pero no little m, que es the unit vector, sino capital M, is the vector ABC. Yes or no? Are you familiar? Are you familiar? Any plane, the normal vector is in the equation. The normal vector is the vector formed by coefficients A, B, and C. Now the normal vector is divided by magnitude of this. And magnitude of this is square root A squared plus B squared plus C squared. And you divide everything. You divide by ABC divided by scalar, que is square root A squared plus B squared plus C squared. And this is the magic formula for finding a unit vector. Cool. In the plane case. Okay. Now let's go spheres. I'm using the interpretation of spheres. Sphere, I know that the equation for the sphere is x squared plus y squared plus c squared equal a. Or radio, a squared. This, of course, this is a sphere. No all the sphere is a particular sphere in which the center is located on the origin, 0,0,0. And the radius a. Okay. So you write the equation in implicit form. Is x squared plus y squared plus c squared minus I squared equal to 0, and you compute the gradient of this. It's obvious that the gradient is partial derivative with respect to x to x, first component, partial derivative with respect to y to y, comma, partial derivative with respect to c to c. You want to find the magnitude of this guy. Is no vector, magnitude. Magnitude is square root. Square root, this guy squared gets 4x squared plus 4y squared plus 4z squared. One more time happen. Can you factor out 4 and outside the radical 2? Entonces 2 square root x squared plus y squared plus c squared. But I know okay, this guy is a squared. Look at the equation. And the square root is 8, so the answer is 2/8. To find the normal vector okay, we need in the flux integral, you divide this divided by this. Entonces ese vector que es divided by 2 es x over 8 because these 2 is cancelled. Chung, 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 comma, y over 8, comma, c over 8. End the story. Entonces now interpretation this is a sphere. It's a sphere. A sphere. And the unit vector is completely radial. So suppose the unit vector, the normal vector, sorry, normal is like that. Boom. Boom. You see que es x, y, z divided by the radius, no? Because it's unit vector. It's completely radial. Radial. Okay, so you consider like a vector field. It's radial, yes? Do you follow me? Sphere?
Yes, sir. Yes, sir.
Go ahead. Follow me, right? Yes or no, Victor?
Yes, we're following.
Okay, good. Okay, cool. Let's move on to the cylinder. To analyze the same thing. Cylinder. Cylinder is, suppose, circular cylinder along the z-axis. Okay, along z-axis. Okay, so we express the equation in implicit. We have no z. Okay, no problem. X squared plus y squared minus c. Minus c, no, we have no c. We have minus a squared equals 0. Cool. Okay. Therefore, we apply one more time the gradient. The gradient vector is partial derivative with respect to x to x. Wow, similar to the sphere. Partial derivative with respect to y. Partial derivative with respect to z. No z. That's 0. So you compare the magnitude of this. Is square root 4x squared plus 4y squared. Now 4 is common factor. I factor out again. Factor out again. Like I do outside the radical, no? Entonces 2 square root x squared plus y squared. Okay, this is a again. This is 2a. If you divide by a, you divide this divided by this. It's obvious that the normal vector is x over a, comma, y over a, comma, 0. Interpretation normal vector. Interpretation. We have cylinder. We have cylinder, like that. Cylinder. Wow, no good. Cylinder. Therefore, my sketch, my normal vector, in any point on the cylinder is like that. Normal vector. Make sense, sir? We have one component x, we have one component y, but we have no component z. This is in the case que es along the z-axis. If along the other axis, it's similar idea, but it's not in this direction, it's in other direction. No? Okay, no back. I understand a little bit. Normal vector, how we compare a normal vector. Now, suppose paraboloid. This is the most popular surface that we use in our problem, no? Paraboloid. Well, paraboloid is suppose z equal x squared plus y squared. One more time, we express it in implicit. Is x squared plus y squared minus z equals 0. Okay, now compute the gradient. The gradient is partial derivative with respect to x, 2x. Partial derivative with respect to y, 2y. Partial derivative with respect to z, -1. And compute the magnitude of this. The magnitude is square root 4x squared plus 4y squared plus 1. But the normal vector is division. This divided by this. So say I copy. 2x, comma 2y, comma -1 divided by this. In this case, no too much simplification. Leave it like that. And that's it. 4 plus 1. Maybe the question that fly in the air is, one of professors say, I solve it in different way. I solve it like that. I put z positive minus x squared minus y squared equal to 0, it's possible, right? We get the same answer, but opposite side. But remember, this is orientable surface, so it's a paraboloid. So I need to find the normal vector or in this direction, or no, in opposite direction. So I go outside or inside. Okay? And you physically, when you determine the normal vector, you investigate si is or is not out or in. Depending on your application, no? Depending on the application you need. Okay? So what is the formula? What is the formula? Formula. Well, this is one possibility. Compute the normal vector. Okay, cool. Okay, another possibility is exactly the same as parametrization. Okay, let me explain parametrization in detail. So our goal is now how we compute this. Now we have vector field dot product normal vector ds, or another version of the same idea is vector field dot product ds, pero ds consider like a vector and ds consider like a vector is m normal vector ds. This is a scalar, the same quantity of this is the magnitude of ds vector is equal to this. Because I know the magnitude of the normal vector unit is 1. Okay, so suppose that we have parametrization, the surface. Okay, vector value function, two variable, you know very well. Entonces es x like a function ub, y like a function ub, c like a function ub. And you compute as always, bueno, you have vector field, que the vector field, I suppose que es PQR in 3 dimensions, PQR. And this PQR is a function of the x and y, the original surface. Now we modification a little bit. First of all, you modify the vector field in order to remember when you set up the surface integral, you need to transform the vector field and you need to find this. So when you transform it, the vector field, well, the only thing you should do is plugging in, no equal here, no equal, plugging in. This is f, x, comma, y, no? The original is given. But you transform it using the new variable, okay, so ub. So you plugging in the vector value function here, u comma b. How we are doing this? Easy, because I know the expression for the x, I know the expression for the y, I know the expression of the c as a function ub, and use substitution here. Okay, so we're using this notation. Okay, cool. And normal vector is the cross product and between the parametrization divided by the magnitude of this. Classic. And ds, que es the other guy, ds, pero ds like that, not like that, is the magnitude of this cross product, the multiplication by du dv. And now we put everything together inside. Everything together is the flux integral in 3 dimensions, is a double integral in the new region R. Okay, remember the new region R is the domain of the parametrization. You substitution the vector field with the corresponding vector value function associated with the parameterization of our surface and the normal vector using this equation que es RU cross RB divided by this multiplication by magnitude. I copy this guy. I copy this formula here and this formula now here. Okay, cool. I can see that this part cancel. The formula that you need to understand is this is double integral in the region R of the vector field under the condition for the vector value function parameterization. Now we have here RU vector cross RB vector. This is a vector. And multiplication by the UDV, que es scalar. Okay, and come back at the beginning. In my imagination, I suppose that this is DS vector. Okay, this is the one way to compute the flux integral using parameterization. I want to explain next class explicit and implicit. It's similar, not exactly the same, but a similar concept of the surface integral and scalar function. Okay, so I suppose que next class we ending the theoretical part. And Friday, important this moment, we start review. Okay, I will send the review part. Cool. No problema.
Cool.
Okay. It's important that you understand the moment that you are living now. This is crucial, important, super important moment, no? And si you fail something, you are in big trouble with me, okay? The student can continue doing very well so far. You end in that part. Unfortunately, I know que I don't know what happened in the movie and the everything, que the last part is the complicated part. Sorry, it's logical, no? This makes sense because you study elementary school, 2 plus 2 equals 4 at the beginning, the first day, and the last day is complicated. So it's obvious. So focus, pay attention, continue working in the lab online, remember the due day, the famous day is July 28. After this day, I close everything. I don't care that you have coronavirus. I don't care. I computed my mathematics. I assign one grade for your job. Okay, A, B, C, or D, or F, right? Okay, guys. Have a nice, good day. We continue Wednesday.
Have a nice day, Professor.